Today we're going to look at the SVD, or singular value decomposition of a matrix. And let's have a look at the sample matrix A over here, 1, 2, 3, 4, 5, 6, really basic. And SVD would factor it as U sigma V transpose. Okay, so what does it mean? U contains the left singular vectors, so the eigenvectors of S left. Sigma is a diagonal or rectangular diagonal matrix with a non-negative singular values, and V transpose is basically the right singular vectors from the eigenvectors of S right. What does it mean? Let's have a look at Sympy to make it clearer. First of all, let's initialize Sympy over here, and then let's load this sample matrix and print it out to get it started. Okay, you can see matrix A over here, and then we compute S left and S right. How do we do this? Just get A times A transpose to get S left, and A transpose times A to get S right. So really basic operation over here, and let's print it out. And you see we get a 2 by 2 matrix for S left in this case, and a 3 by 3 matrix for A transpose A, which is S right. Okay, the cool thing is you can do this for any type of matrix, so the SVD always works, and it doesn't have to be a square matrix, but you will get two matrices of different size, and this will matter, as I will show you below. So next up we will compute the eigenvalues of S left and S right. This is easily done by just using the command .eigenvalues in Sympy and get the keys, and transform it into a list. So we get this for S left and S right. Let's print it out. And the eigenvalues of S left, so as mentioned, A times A transpose, and S right, A transpose A, would look something like this. And now we have to do two things. We have to first of all extract the common eigenvalues between the two matrices, S left and S right. As you saw, they have different sizes, so they can have a different amount of eigenvalues. We want to have the common ones that are greater than 0, and also sort them in descending order, because the size of a eigenvalue or singular value actually says something about its importance. And usually by convention, we sort them in descending order. So we have the top ranking one at first position and the lowest ranking one at the last position. Okay, so we do this over here. We get the common eigenvalues, val for val in eigenvalues left, if value is greater than 0. And we also compute the singular values. So to do that, actually, there's one thing. We have to take the square root of the value in the common eigenvalues to get the singular values. Okay, and then we print this, and you see that we get the singular values. In the manual calculation would look something like this. And now we can basically set up the matrix sigma by adding the singular values to the diagonal of sigma. And so first of all, we set up an empty matrix which just is filled with zeros, and then put in this position 0, 0, 1, 1, we add the singular values. So they will show up on the diagonal of the matrix. And also there's a standard Sympy method to do the same thing. Just to prove that I get the same results, we can use the standard method by just saying a.singularValues and compare both results. So let's see what this gets us. We have sigma over here, see, and this is the same as we get with the singular values command. This is just not shown on the diagonal as a matrix, but it's the same singular values. So that's great, that's working. And to also show you that we can actually rebuild matrix A from SVD, I will show you at the beginning, as I mentioned. So this is basically, these are the same. We can do this in Sympy, but it's a little tricky to do it, and it's easier to just do it with NumPy, because I had some pre-built commands for it. So let's use NumPy instead here to show you how that works. And we're importing NumPy, and I'm loading the same matrix, 1, 2, 3, 4, 5, 6. And then we compute the reduced SVD. So we can just use the standard command linear algebra, so linalg.svd, give it the matrix, and say we want to have the full matrices and write the result into these variables over here. So UMP, S, and VHMP. And then we have to still construct sigma because this just gives us a list and we want to have it as a diagonal matrix. So we just say np.diagonal S to obtain sigma. And then just when I run this command, so we get U times sigma times V transpose, it should give us the same matrix that we had at the beginning. And as you see, original matrix A and then the reconstructed matrix is exactly the same. Yeah, since the SVD is super important and shows up everywhere when working with data, I just wanted to walk you through these examples. This is not how you would compute it in a prod environment. It's more focusing on the general mathematical concept behind it. So hope this was useful and see you again soon on this channel.